Hello. Yeah, let me just this one. Okay. Hello. Hello everyone. I'm gonna in this video I'm gonna discuss about the p-value. Okay. Before we go to the p-value, let's just think about this the contingency table here. Okay. So this is the exposure, and then this is the outcome, right? So this exposure is positive, and then the negative outcome can be positive or negative, right? Then if the exposure is positive, then it's a true positive, false negative, false the true negative. That's what we are familiar with, right? This is just a regular contingency table. Now, suppose we are developing a new the drugs. So you plot the, for instance, if you plot the pain reducing scale. Okay, so pain, maybe this was like a pain reducing scale, and then this is like the drug amount. I mean, this is the number, the patient. So patient number one has like other maybe this much pain scale, and then this much reducing, and all these kind of things, right? It can be anywhere in here, right? So it can be this one, and you just summarize it as the in kind of in the order. Then it will be like if it's like a pain scale, we'll say the mean is here, and then there will be some other data point here, and then here. Like if you the more data samples you collect, it will become more like this the normal curve, right? So this was like the current or old the drugs. Okay, and then if we are now testing with the same testing with the new drugs, then it will be another drug like this, right? So when we it's kind of randomized control trial. Now we draw this two normal curves here like this. So this is old, and then this is a new drug, right? Then the question is, okay, is this really is there any the difference in this the mu here, the mu2 here, right? So the question is, are these same or are these different? That's the question. Okay, suppose like this was graph is like this. Okay, as pulsars to one another graph is like this. So is this like the old one and then new one, old one, new one? Is this does the new drug has any effect or better than the old one? In this case, is this the new drug is better than old one? It looks like this one is better, right? But how can you prove it? That's the question. Okay, so the way you prove it is whether they are the overlapping or not overlapping. So that's how you got p-value. P-value simply means that are these two normal curves overlapping? Overlapping. That's the question. Okay. So now, if you overlap, how much like the chance? What's the probability of this being overlapped? Two graphs being overlapped. That is the question. Now the this to understand that we need to understand. Let me see. Let me use the real pencils instead of this one. So here this contingency table, true positive, the false positive, true, I mean false negative, the true negative, right? So this is the beta, 1 minus beta, alpha, 1 minus alpha. So this is in hypothesis testing, H1, H1, H0, H0. Okay, so what this means is that when H0 means the two the one drug, old drug, and then new drug has a no difference. Basically, this is same, and then there's a different, meaning that the drugs, the new drugs, effective. Okay, So that's what the test result. Test say, okay, the new drug is effective, so more effective than old drug, and this H0 means that test says that the new drug and old drug has like basically the same thing, and then this is the truth. So is new drug really has an effect, or like truly, or it's just the no like they are same thing. Okay, so the way you, and then let me just label this one. Okay, so this is the 2-by table, right? So beta is a type 2 error, alpha is type 1 error. This is 1 minus beta is power. Okay, so alpha is a significant level. So depending on the significant level, we can decide whether we accept H1 or we accept H0. Okay, so what do you, but in hypothetical testing, they are not that nice. The statisticians, for some reason, they are very, very kind of, negative people. So what they do is, instead of saying accept H0, we say we fail to reject the H0 or fail to reject H1. It's they are very, very, everything is like a kind of, negation, negation, negation. So that English terminology and the negating things will make it look complicated. But if you draw the contingency table in this way, instead of what mostly the thrown in other literature like first aid or other resources, they throw it in different, sometimes they call it H1 here and then the H1 here, and that doesn't, it's not really consistent with the contingency table we are familiar with. This is what we are familiar with, right? So we, based on this, A, B, C, D, and then we all kind of statistics calculated from that, right? But then all of a sudden, then when the hypothesis testing section, if you look at it, then the first stage is a different arrangement of this thing, this thing, this thing, this thing. So that makes more difficult. But let's just make it very, very simple here. So now, so H0 means that simply the test is same. Okay, and then so if it turns out that test says that it is same, then we just look at only this row. So can you make the type 1 error here? No, you only make type 2 error, right? If it's the H1 is true. Now then, what in the question vignette, how do I say that H1 is true? They don't say like, okay, the truth is the H1. Though they don't say that. So the way they do is kind of weird. The test, for instance, the researcher is what, for instance, what error did the researcher make? What did he make? Then what error he makes? So there was an error, right? So that means that, okay, test come out to be there's no difference. And then what error he made? So there is an error. So the only possible way it can be error is because the test is H0. If the truth is H1, then you made the error, right? So then this one, you can say that, oh, the truth was the H1. Okay, so that's the error. So that means the type 2 error occurred, right? Or sometimes they can ask you what kind of error the researcher will avoid. Then you avoid the type 2 error. In other words, that's the test result coming out in this same. So we are looking at this row. Now then the test was avoiding the error. So that means there was no error, right? So then the truth is H also H0. Okay, so we can deduct from the question vignette. Okay. So that's how I do it. How do you do it? And then this p-value is something to do with the significance level. So if the p Normally this is like 0.05. For simplicity, most of the time they use a 0.05, but sometimes they use 0.01, something like that. Okay, so now the going back to this the here the two graphs here, right? Mu1, mu2, right? So and then there's associated the standard deviation, right? The standard deviation. And standard deviation here, standard deviation here, standard deviation here, right? So the way here S1, S2, S2, right? So the way there's a like formula to see the difference between this comparing these two normal curves. So this formula usually is more involved. So I'll just write it down here, but we will probably never have to calculate this actual formula. So which is mu1 minus mu2 plus minus, because you know the it's a confidence is like this will give the confidence interval of the two normal curves. The mean difference of mean difference. Okay, so confidence interval of two normal curves of mean difference, because of, mean is our the main statistic. Okay, so this plus minus, and then I'll give you this this number like blank here times square root of big square root of the S1 square N1 plus S2 square N2. S1 and S2 is like a standard deviation here, right? And then N1 is the number of N1, number of samples in the old drug and the new drug. Okay, old drug trial and new drug trial. So this thing is called T statistics. What the heck is T statistics? T statistics is the you can find this value from the back of the statistic book. So what this means is that comparing this the normal two normal curves is called student T distribution, meaning that these two T statistic doesn't make sense if it's only one the curve. It always makes sense comparing the two normal curves. Okay, actually it could be more than two, but you know, for simplicity, let's just assume it's two. So comparing these two statistics, so this T statistics can be 1.65, 1.96, and then 2.56. Okay, this is when there's a 90% confidence, and this is a 95 confidence, then 99% confidence. Okay, so because we normally use a 95 confidence level, so this is this can be 1.96. Okay, so this is the formula that calculate the mean differences between these two samples. And then if this value turns out to be that's the value to find out the p. Okay, it's not exactly this will give you the p, but this will kind of this will just convert to the p. Okay, p values. Okay, this p value compare this alpha. So if p value is less than alpha, for instance, alpha was 0.05, and then p was like say the 0.001. Okay, then it's less than 0.05, right? In this case, it is called statistically significant. What significant means is that it is this two graph here, and then this thing is significantly, the mean difference is significant. There is a effect. So in other words, this new drug has an effect. It's a good effect, so that it's much better than, superior than the old one. That's what that means. Significant means. Okay. So if it's on the other hand, if p-value is greater than alpha, so for instance, like p is 0.3, okay, then In this case, we call it statistically insignificant. That means that the old drug, the new drug have no effect difference. They are basically the same thing. Okay, so in world, what this means is that p-value means is that probability of two curves overlapping is p-value. So in other words, this is point say 3. Then probability of overlapping these two curves are like this. So it's very much overlapping, right? So what's the chance of this? You randomly select one point in here, and then randomly select in one point here. They are kind of in the water, they're basically in the difference curve within that the range. That's the whether they are overlapping. Okay, but if one graph is here, one graph is way back there, then the chance that this overlapping is very, very tiny, right? Can be overlapping like this, but very, very little bit, right? So for instance, p equals the very, very low 0.0001. Okay, then these two graphs are very, very far apart, but only very, very small chance that they can overlap. So in that case, statistically significant. What that means is that we can assume that the new drug is statistically better than old drug. Okay, so that's what the p-value is. Okay, so basically it is a measure of the mean difference in based on this the formula here, but which you don't have to calculate it, but it's basically this depending on the t-statistics, which is already calculated and charted in the back of the US statistic books. Okay, so make sure that you know this, you understand this the hypothetical testing and the constructor table in H1, H0, H1, H0. Like this is testing, this is a truth. Okay, and depending on the read the question vignette that whether it says testing says that they concluded they are all same thing, right? They concluded that there is no difference here, or they concluded that the new drug is better than old drug. Then you are looking at this top rows. Okay. Now then because they don't explicitly say the turns out that H1 is true. They don't say that. They will say that what kind of mistake the researcher made, or what kind of mistake the researcher avoided. Okay, so from those kind of the vignette that you can determine whether they are talking about this row or this row, and then whether they are talking about the H1 or H0. Okay, so it's all kind of matter of interpreting the wordings from the question. Okay, I hope this helps, and thank you very much for watching. And then it will be very, very helpful if you subscribe, and I will upload many new videos topic by topic. Okay, thank you. Bye bye.